Now, first of all, we always factor x plus 3 and x minus 3 over 2x. And that, it's easy to see we have a non-permissible value. X can't equal 0. It doesn't cancel out. Anytime something doesn't cancel out as a vertical, as a non-permissible value, it becomes a vertical asymptote. Question asks for your y-intercepts and x-intercepts. Well, here for a y-intercept, you're going to have none. Why? Because you can't plug in x equals 0 if it's a non-permissible value. So there's going to be no y-intercepts. But our x-intercepts are easy to find since we have the top factored here already. And the only place, when you plug in 0 for y, the only place a fraction is equal to 0 is if its numerator is equal to 0. So that's at negative 3, 0, and at 3, 0. Now, if we, like this question just asked for x-intercepts and non-permissible values and y-intercepts, but we were trying to graph it, notice that the degree is larger on the top than the bottom. So we will have an oblique asymptote. And some of you, after plotting points, noticed there was an oblique asymptote, but finding this one's a little bit difficult because you're not allowed to use synthetic division if you're dividing by 2x. So if you can't use synthetic division, you would have to use long division. And I have to ask myself, what would I multiply 2x by to get x squared? You would have to multiply by 1/2 x. 1/2 x times 2x is x squared. And that's the only thing you'd have, so you need to subtract. If you subtract, you get 0 plus 0 minus 9. No more x's left, so we just have our remainder of minus 9. So we have our oblique asymptote at y equals 1/2 x. So this part of this equation is new. What's interesting in graphing these is we follow the steps the same way every single time, but we keep running into new situations, which makes it a hard unit that way. Easy because you have to follow the same steps, but hard that you keep running into situations like, oh, this is weird, and then you feel like you should stop, or a little bit not confident. But if you follow the same ideas all the way through, I'll tell you that it will work out. So if we look at what we have here, we can draw in our asymptote at the non-permissible value x equals 0. We can use the slope of 1/2 and draw the asymptote at y equals 1/2 x, and we can plug in our x-intercept at 3, 0, and at negative 3, 0. This is enough to draw your final graph towards the asymptotes. For part B, or not part B, but first of all, for the second one.
I have a question.
Yes.
It says, so if we put the oblique asymptote at y equals 1/2 x,
Yeah.
so if you put in x equals 2.
Mm-hmm. You put in x equals 2.
Oh, wait, no. Oh, all good.
It's all good. Yeah, but if you put in x equals 2, you will get, pending a mental math mistake, you'll get a point somewhere down there, right? 2, comma.
Okay, yeah. Apparently I messed up some minus.
Okay, and that's fair enough. The bottom factors to x minus 3, x plus 1. So we have non-permissible values that x can't equal 3 and x can't equal negative 1. They don't cancel out. So they become vertical asymptotes. This one is easy to find your y-intercept. Plug in 0 for x. Simplifies to 2/3. And our x-intercept is easy. The only place your numerator would equal 0 is if x is 2. If we are graphing this, we also need to find out if there's horizontal asymptotes or vertical asymptotes. This is the situation where the degree is bigger in your denominator. And anytime your degree is bigger in your denominator, you will have an asymptote at y equals 0. So going to sketch this one, horizontal asymptote at y equals 0, vertical asymptote at -1 and 3. Y-intercept at 0 and 2/3, x-intercept at 2, 0. Now, we would know this has to go up, because it needs to go through those 2 points, and it needs to go towards the asymptote. If it went down towards the asymptote, you would introduce another x-intercept. But we found all the x-intercepts. That's one of the important things about finding the x-intercepts, is that once you've found them all, you can't make more of them. And there's a couple of ways you can determine this part. It's going to go down towards the asymptote. We know that it's going to go down. Either you'd have to plug in a point, a nice point like 2.5, and find out where that is. Or you could see that your x-intercept at 2 has a multiplicity of 1. And if an x-intercept has a multiplicity of 1, then your graph goes straight through. So we can use that information from chapter 1. How do we know that it has a multiplicity of 1? Well, if we look at it here, right, it only happens once. If you had x minus 2 squared up there, there would be a balance. Okay? We're going to see a balance today with some questions like that as well. Okay? Now, obviously, we don't have enough, so we need some other nice points. And sometimes you look, I don't have a point in this section, I don't have a point in this section. So I'm going to need to plug in -2, and I'm going to need to plug in 4, and find out what those values are. So I go back to my equation. If I plug in -2, the top will be -4, -5, and -1, -4/5. If I plug in 4, I'm going to get 2 on the top and 5 on the bottom. So plugging these points in, -2, -4/5, and that's enough to draw that section, and 4 and 2/5 is enough to draw that section. And finally, the construct the understanding question. Again, we start by factoring it. Difference of squares on the bottom. And this one simplifies. So, we list our non-permissible values. Still, x can't equal -1 and x can't equal 1. The -1, the one that doesn't cancel out, will become a vertical asymptote. The one that does cancel out will have a hole And it will have a hole when the x-coordinate is that non-permissible value of 1. Now, a couple of things that are mistakes that happen in this question, okay? When things cancel out, you should rewrite what the new simplified version is. And this x plus 1 is in your denominator. It stays in your denominator. And you would have 1 over x plus 1. So many times I see this cancel out and everybody's like, ooh, I just have x plus 1 left. And they write y equals x plus 1. This is your new equation. And from now on, this is what you have to graph. And this example is the first time that we have a hole in a graph that's not a straight line. I don't know if you've noticed. So far, if you have a hole in your graph, they've all been straight lines. Okay? This one is still a rational equation. So because it's a rational equation, we still have to do the steps for rational equations. Does it have a horizontal asymptote or an oblique asymptote? Well, the degree is bigger in your denominator and anytime the degree is bigger in your denominator, you have a horizontal asymptote at y equals 0. Find our x-intercept and our y-intercept. And from now on, we use the simplified, we're graphing the blue one and adding a hole. We're no longer, well, we're still graphing the original, but for our steps moving forward, we use the simplified version. So if I plug in 0 for x, I get 1 for y. But here's where it's important. If you're finding your x-intercept is where your numerator is equal to 0. Can you see our numerator is 1? There are no x-intercepts. But if you use the original equation, you might be tempted to say there's an x-intercept at 1, 0, but that is your non-permissible value. So we have to be careful with that. Okay? We still need to find the y-coordinate of our hole, and you find your y-coordinate of your hole by plugging in the non-permissible value into your new equation. Isn't hard to calculate now, it's 1/2. So we photograph. We have horizontal asymptote at y equals 0. A vertical asymptote at x equals -1. Our y-intercept at 0, 1. Our hole at 1, 1/2. And so we have enough in this section to draw this. We have nothing in this section, so we need another point. I'll plug in -2. Again, I plug that -2 into the blue equation. Label all of these points. And this is our final graph. It's a rational graph with a hole. In fact, you can have any graph you've ever had before and add a hole. If you want. I can add another hole to this. Like, if I added x minus 2 on top and x minus 2 on the bottom, that would cancel out. There would be another hole here. You could add 15 holes to a graph. Take any graph that we've done so far. Take x squared plus 4. Problem, you've got 4. You want to add a hole to it? Put an x plus 1 on top, x plus 1 on the bottom, cancel out, and then you add a hole to that graph. So we can have holes in any graphs that we've done so far, as long as something cancels out. That'd be a good exam question. A log graph with a hole in it? No? Okay. So, the other thing I want to point out is the blue graph We graphed it as a rational graph. You could have graphed the blue one using the very first chapter that we did. One of our parent graphs was 1 over x. Remember transformations? This plus 1 would move your 1 over x graph 1 to the left. Can you see that its shape is the 1 over x graph? It's been moved 1 to the left. And we added a hole to it. Okay.